a problem which is bound to arise if you implement a hidden Markov model and you run it on some non-trivial length data like n equals, if you have like n equals 100 data points or so, then you're bound to run into the problem of underflow. And underflow is when you're trying to represent a number on the computer and it's too small for your software or for your computer programming language to represent. I mean, some computer programming languages will automatically, allow for arbitrarily small numbers, but a lot of computer programming languages do not. And so when you get a super small number, then it just sets it to 0, and so you end up computing the wrong. The result you get is going to be wrong, and this is a very sort of subtle problem that you can run into, and this is a very important thing to be aware of. So this is a very important video. So fortunately, underflow can be fixed with what's called the log-sum-exp trick. And so how does this happen? So let's think about this in the context of the hidden Markov model. This problem happens a lot, for a lot of algorithms when you're multiplying lots of things together. It always happens when you're sort of multiplying lots of things together, and so you end up with things that have very small probabilities, or whenever you have things with very small probabilities. So let's think about, in the case of the forward algorithm, we had these things. We were computing the probability of z, k, and x1 through k. And so when k is very large, like n in particular, this is going to be a very, very small probability, because the probability of getting any particular sequence of x's is just so small. So this is going to be a very small probability. And let's write down the formula for this and see if we can fix it. See if we can see how this happens. So the formula well, okay, so before I say that, maybe let me just say that, so in general, since this is a small number, the thing to do when you want to represent a very small number is take the log, because the log, if you have like e to the minus 1000 or something, and that's way too small, then when you take the log, it's just minus 1000. So that's not too bad at all. So the thing to do is to take logs, and let's see what happens. Not just take logs, there's another trick that you have to do. But let's see what that looks like in the case of the forward algorithm. So we have this sort of, let me write here. What am I doing? So I'm just going to copy this formula from the video on the forward algorithm. This was the thing that we had to compute at each step. Alpha k minus 1, z k minus 1. Okay, so if we take the log of this, if we want to work with the logs here, I guess this was alpha k z k. So let's just put that. We're going to simplify this down in a second to the core of the problem, but I just wanted to illustrate what it looks like in the case of the HMM, so you see how you use it. So this is the log of the sum, and then if we're sort of switching representations to logs, then this is going to be exp of the log of these guys. Log alpha k minus 1 z k minus 1. Okay, so we've got this, and if we're working with the log of the alphas, because the alphas we're just too small. So in our computer program that we're writing to implement this, instead of representing the alphas, we're going to represent log of the alphas, because they're easier to handle. Well, we can store them in the computer without underflow. And so to do the forward algorithm, we need to do this step. We need to do this sum. And so let's think about here. We have log of alpha k minus 1, and that's all good. And we add some stuff, and that's all good. But then we have to take x. We have to take e to that. And if alpha k minus 1 was small, then this is even smaller because log of a probability is a minus number. This is even smaller, so when we take e to that, if this was going to underflow, then that's certainly going to underflow. So there's a problem here. And so here's how we're going to fix it. So let's think, let's abstract this a little bit. Let's think a little more abstractly, simplify the notation here. Let's call this, so the basic thing is we're summing over some things here. Let's call this I, and let's say we're just summing over, let's call this xi, and let's say we're summing over I. So we want to compute this. So the thing we want to do is we want to be able to do an operation like this. We want to take some x's. This is different x's than before. Maybe I should have used a different letter. Maybe I should use A. Let's use A. AI. That's better. So we have these numbers, A1 up to AM. I guess it's actually AM. And we want to do compute, so we're given these, and our task is to compute what we need to do. Compute log the sum of the i's e to the log sum of the log of the ai, or is that right? No, sum of the, so it's just e to the sum of the ai's. Wait, is that right? Hold on. Oh, sorry, not the sum of the ai's. We already have the sum of the ai's. It's just e to the ai, of course. I'm sure you saw that. Okay, so we need to compute this. This is our task. But we can't just do it directly because e to the ai could be very, very small. So what do we do? Well, this operation here on numbers, like on these numbers, it's actually approximates a max operation. This is approximately a max operation. So this thing is actually roughly, this quantity is actually going to be roughly max of ai over the i's. That's weird. It's max over the i's, roughly speaking. And in fact, sometimes people use this operation to approximate the max because you can differentiate it and stuff like that. So with that sort of intuition, we would think that only the largest values of the AIs are going to matter because it's roughly a max. If the AIs, and we can see that directly from the formula, because say that A1 was a big negative number, if it was very small, then e to that is going to be super, super small. And e to the larger ones is going to be relatively larger. So with that motivation, let's factor out the largest guy. So let's factor out e to the, let's call it b. We're gonna derive a formula here, so that's ai minus b, where b is max over I of ai's. And now log of the product is the sum of the logs, so this is b plus log I from 1 to m e to the ai minus b. And now we're in pretty good shape, because so if b, so the AIs are going to be negative numbers typically. So minus this, we're actually adding some number here. Minus b is actually a positive number. So the picture is, the intuition here. Can I draw a straight line? Apparently not. That's a little bit straighter. The intuition here is that we had all these these very, very small, these very, well, I guess small. They're large negative they're negative numbers of large magnitude. And we wanted to, so say this was like 0 here. And we wanted to be able to take e to these, but maybe e to these is always like way too small. It's always 0. So we shift them. We shift them. And we shift the largest one, so the largest one gets shifted to 0. Largest one gets shifted to 0. And then the others get shifted accordingly. And that's what happens when we subtract b, because minus b is a positive number. We're shifting. We're shifting by exactly this distance. And so when we take e to this, okay, some of them, like maybe this guy is still way too small, but it turns out that it doesn't matter, because he's not going to affect the result very much. He's going to affect the result in an extraordinarily minuscule way. He's only going to affect the result in a way that would not even show up in the precision of what our language can compute. So this is good. So these numbers here, some of them may be very small, but the ones that matter, the ones that are going to affect the result, are fine. They're not going to underflow. So this is just what you do. So you do this. You subtract off b. You shift to the right. So boom, that's this part. You take the sum of those numbers. Of course, that's no problem. Then you take the log, and logs are always nicer than not logs. And then when you add b, you're shifting everything back to its appropriate place. So it's shift to the right. You do this, and then you do the sum. You take the log again, and then you shift back, and then you get the desired result. So this is the trick. So you do this here. In order to compute this quantity. Maybe I could. So the trick is, not just taking logs, using logs is important, but also the important thing was the shifting thing that went on to make sure that in the process we weren't losing something which was important. So this is an important trick. So I called it the log-sum-exp trick. And of course, here you can see there's a log and there's a sum and there's an exp in there. So that's why it's called the log-sum-exp trick. But that doesn't really tell you the important part of the trick. The important part of the trick is this shifting thing. Okay, so this is an essential tool that you will need to use if you are ever to implement a hidden Markov model and run it on on data of non-trivial length. So that's the trick. And so it's kind of funny. The first time that I actually, I noticed that this, before I really was doing, using all of this stuff, but I happened to be, before I knew about this trick and before I was really into machine learning stuff, I came across this function and I was writing a program, and my program involved this, and it was approximately this. I was getting these weird results, and it was like always approximately the max. And so I plotted out, for a bunch of values what this function was doing. And it was like exactly the maximum, because of the scale. I was at a sort of large scale, and it was the maximum. And I was just stunned. Here's, this is a smooth function. This is just a beautiful, smooth, infinitely differentiable function. And so it's just a really, really cool fact that this is approximately a max. Because oftentimes, because a max is a non-smooth thing, it's a very sharp, non-differentiable guy. And so the fact that you can have a smooth max like that is a cool fact. So I just wanted to point that out too. Okay, but that's log-sum-exp.